And we are now live downtown, but except none of you can see the board, I just realized. And oh, which one? That is
two numbers that multiply. These three. Are you drawing Google? No. Do whatever adds to the
Bruh. What the heck am I doing?
Or you can put the two outside of the brackets. Two doesn't apply for all of them.
Okay, any questions on either one since you have them on? Okay, put those away, close your laptops. We're ready to go. If you could double check your your nucleotides from last day. You don't know their codons yet. It is just on the board. The one to check, if you want to check yours, is that one, because that is also a match to the reading strand. These two should essentially be the same, except everywhere you see a T up there, it should be a U, and it should just run right along, because if your T going to A goes to U, C goes to G, and so on and so forth. And the same, of course, would have up there. This is the DNA, that is the messenger RNA. And now that we've made this snippet, this process is called what? What did we just do? It's transcription. So this was transcription. Now we have to do some translation. Translation is a little bit more complicated. Transcribing, you're just copying it. Relatively simpler process. In this point, we have to bring something that is fundamentally different. also intensely dislike how they do this because it always starts with AUG. Anyway, this is technically, as it says there, a ribosome. There's a piece down here. That's the small subunit. And that one here of the ribosome is the large subunit of the ribosome. The ribosome is actually made of two halves, and so they both come together and lock in. And when the mRNA leaves, it comes to a ribosome. And where is the ribosome likely to be hanging out? Where do you find ribosomes in the cell? Yeah. So we've got the rough ER or the cytoplasm. There are ribosomes just floating around doing their job. We now have a new type. Now, I did like this diagram because though it was colored and I thought it was fairly clear, but they did get one thing wrong. This is not tRNA. Here, let me color it in yellow. Nope, wrong yellow. Pretty bright yellow. Okay. Oh, better. And you'll probably be a little annoyed by this. It's not tRNA, but tRNA. Make all the T's lowercase. And while I'm being pedantic, it's to recognize tRNA is a different kind of acronym, and we lowercase the first one to emphasize that that is for its function, but RNA is the name of the molecule, so it's still a ribonucleic acid. But it is a tRNA. This is what happens when we get non-biochemists making up diagrams. Or transfer. RNA. We have the mRNA sitting pretty here with the ribosome. And it is read in 3-letter segments. So you'll notice every one of these has 3 letters. And it matches complementary pairing to the messenger RNA. So if this is AAA, A goes to UUU, and so that they can bond. Someone, I don't know if it was in this class, asked, well, why doesn't RNA have a double helix, or at least a ladder structure like DNA? And the answer is the hydrogen bonds are just a little too weak to do that as a permanent structure. But they're still there, and they can do it as a temporary structure for a little amount of time. Those 3-letter segments on the mRNA is known as a codon because it is part of the code. The tRNA, here, this, that, is an anticodon. And I'm going to put that there anyway, so I might as well do it now. So tRNA floats in. It is carrying, those of you that mix up powders might know, Phi, asp, lys, terp, what are those? No, they're smaller than enzymes. Some people take powders and they mix it and then they drink it. Proteins. Specific, what part of proteins? Because it's not actually often proteins. It's smaller than a protein, but you use it to make protein. Amino acids. In the same way that a nucleotide builds DNA, amino acids build protein. They're individual building blocks. So people will make up protein drinks that are amino acid drinks. And that way you are drinking the pure amino acids that you need to build muscle. You don't have to break it down first. When you eat protein from, you're having some chicken or some chickpeas, either way, you're taking the protein and you're breaking it down to its amino acids in your intestines. You absorb the amino acids, and then you use that to build whatever you want. So essentially, you're just stealing all the building blocks. If you mix up the powder and they're building blocks already, it's absorbed a lot faster. You don't have to break it down first, and you know exactly what building blocks you're getting. One codon codes for one amino acid. And what kind of pairing is it called when you have like A to U or G to C? It's something you tell someone when you're being nice. Complimentary. Function of tRNA. So the job of tRNA is to pair with anticodon with the correct codon, and its job is to bring that particular amino acid. So there's individualized tRNAs, one for every type of codon that carries a specific amino acid that matches with that. Peptide is a single amino acid chain or a small protein. Did I misspell protein there? Yeah. No. So it's made by a ribosome. It's one single chain, and we can call it a peptide. The reason we make the distinction is things like hemoglobin, which is a protein inside of your blood that carries oxygen, is made up of multiple amino acid chains, and they all get put together in a larger structure. So the coded message, tRNA or mRNA? mRNA. So that's the code. This helps read the code. There is one other type of RNA, and that is rRNA, or ribosomal. Helps ribosome and it just helps the ribosome stick to the mRNA. So if we were to represent it as a little pink line, in the ribosome, you would have this little bit of RNA in there that's helping it stick. Anybody still ready? No, huh? Okay. Let's get that out of our way a little bit. And don't write anything down just yet, but we are going to go through the process. A, U, G, 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 You'll notice I've put little spacing so we can see the codons. That, of course, is not normally present. That's just for our eyes. I'm going to draw. Oops. No, that's Control Z. Excellent. Ooh. Oh my goodness. I already have it. How much of it do I have though? Yeah, I can get rid of that one. We'll keep that though. That looks useful. And oh yeah. And, nice. How many of these we got? You probably didn't think you'd hear me say this again. However, get out your data table. Is there more? Nope. Not yet. I mean, no. Okay. Everybody have their data table out? Turn to the biology page. Your biology page is fairly easy to find. It's on the very, very back page. This is a codon table. Using this table, you can figure out what every amino acid is coded for. So, we have our reading strand from DNA. Transcription happens, floats out to the cytoplasm. Once it's at the cytoplasm, ribosome sticks to it. This is known. Oops, I'm not going to. No, I want it a different color. First phase of protein synthesis is initiation, where the ribosome attaches to the mRNA. Draw that. You are nope. You're not writing the DNA down. You're not writing all the garbage over here. Just this. Just this. These are lies. You can read. You're just saying that to make me feel bad. That says, no, that does not say that.
No, it's because I didn't bring glasses today, so.
Oh, thank you for spraying my thingy. Does it say this one? Nope, doesn't say that either. Okay, maybe my writing was too messy.
It just said initiation. Did it?
Yeah.
I don't know.
Initiation.
Okay. My eyes are too cooked from playing.
Oh, yeah.
What? Howard, Marvel, Ryan.
Even Ryan Nash's guy. You know
Language.
Grandmaster. No. It's a rank. It's like.
Nope. Okay. Oh, I probably should warn you. You will need room to draw this 3 times.
On the specific page.
Is that
Or get out a separate piece of paper. Yeah?
like in the second codon? Is that a GGC?
GGC.
Gallimard. Just reminded me of the time.
Okay, anybody still writing? Pardon?
When you write the words.
Where it makes sense. I wrote it at the top. You can write it at the top.
Well,
You're labeling this phase.
Oh.
Because I'm going to erase it. And then we're going to do the second phase. Alex, Ariel, Charlie, Sal, Guy, Isaac, Isabel, Jessica. Well, I think we're all here. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16. Okay. Anybody still ready? Perfect. I am now going to get rid of it. Delete. Delete. We're going to write it again. Now, this is the codon. What is the anticodon to that codon? TAC. And the anticodon, using your table, what amino acid should it carry?
What table? Yeah, what table are we on?
The one I just told you to get out in your data table.
Wait.
In your data table,
Wait, it's according to the codon?
it's according to the codon.
And in this codon, it's AUG?
Is A,
UAC. Tri-Ross.
AUG.
How about GGC? Is that?
No, first one. I'll start with the first one.
Just the
Methane.
first one.
Tri-Rossine. Is it methane? Tri-Rossine.
Try, check, nope. Methionine. It is often amusing to hear people try to pronounce that. So, floating.
UAC,
No, 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 no.
is it not UAC?
Not UAC is the anti-codon.
Yeah.
This
So we're looking for
is a messenger RNA codon table. So you look up the codon, not the anti-codon. So, can you find AUG?
Oh,
Yes.
so AGU,
AUG. Now, notice the little star beside AUG? That is always the first codon. That is how your body knows where to start. It is also back in the DNA. We'll talk about cataboxes, which signal the start of a DNA. And the DNA always starts, a gene always starts with TAC because the messenger RNA is always AUG. So methionine is the first amino acid of any protein. And so tRNA comes. tRNA. Why are you not? You're not floating with. Yeah, I allow move and rotate, so you should be. There we go. Nope. I have to unlock it. So tRNA floats around. Comes into the ribosome. There's a little hole there. It's a little smaller than the tRNA, but size isn't everything. And the amino acid is waiting. What will the next anticodon be? It is GGC, CCG. So we put CCG and let's group that. Group. What amino acid would it be attached to? Lysine. Hold it. Where's my lysine? I didn't get a lysine. I wasn't expecting one. Glycine. GGC is definitely glycine. Did you say glycine? Oh, I heard lysine. They sound the same. Okay, this one comes down. And good. Okay. Now you have two amino acids next to each other. Yes, question? Okay. Two amino acids are now next to each other. They've been brought close together by their friends. You can think of it like a blind date. They look at each other, sparks fly, and they bond. Hold it. What kind of bond should it be? It should be a pink bond. Because pink is for peptide. The bond between amino acids is a peptide bond. It's just a covalent bond in terms of what we've done in chemistry, but it's this particular type of covalent bond, and we'd like to make it feel special. So, one. Pardon? Oh, no, not yet. No. This whole phase is known as elongation. I should put a 2 there. tRNA binds anticodon to codon. Amino acids form peptide bond. Ribosome moves one codon. So now You're not going to believe this. But the whole thing goes. Chuck. No, that whole thing was supposed to move. And are you also a locked thing? No. Why did the whole thing not move? I want that one. And I want that one. And I want the whole.
Why don't you bring both out and then just do that?
I'll just move them one at a time because it's getting dumb. It goes cha-chunk, cha-chunk. Now what happens?
Another repeats the GAU.
Yeah. What is the anticodon to GAU? Oop. Control Z. Now, someone already said aspartame, so I might as well grab that. So we got some aspartame here. And what was the anticodon? CCC. If you put a P on the end, it would be Russian. So this is floating around the cytoplasm, comes in, ching. Now, while that is happening,
Why is it CCC?
oh, I was reading that one, and then someone said it out loud. It's not CCC. We'll save that one for later, because we're going to need it. What is it? C CT CUA. And what amino acid is that? GA.
That's aspartame.
Yep. They also confused me with the aspartame. There we go. Gentlemen, Twilight Princess is not currently part of blood protein synthesis. And if you want to do your broning outside of class, broning. People who are really into My Little Pony. Bronies. Okay. What happens now? It bonds. Chunk. And what's left over here that's not needed?
The ribosome.
No, ribosome's still bonded, still used. What doesn't need to be bonded anymore?
The
The first
AUG.
one?
The AUG is still attached this way. It's not going anywhere. No, the MET's attached.
What's it called? tRNA.
The tRNA. It's not needed. It did its job. It's brought the amino acid. That just floats away. Ribosome moves one codon. tRNA detaches. Once peptide bond formed. Excellent. What would it do next? It would move on to the next one, another one would come in, and then it would form the bond and it would go. So now we have repeat. Excellent. Draw this. So now this, draw elongation. Your best interpretation in the middle of elongation.
For which one are you drawing?
Pardon?
For which part are you drawing?
Well, all of it, except for you have to draw that. Oops, you have to draw that, and you don't have to draw this. Well, we haven't gotten to glycine yet. We haven't gotten to that one yet. Oh, that can all just be deleted.
So which part do you want?
There you go.
Just that?
Draw all that.
Draw a mess on the patient.
Yeah.
I guess I can copy it.
I'll take that infinite chlorine away, put it up there, and maybe give myself some room. And maybe make it a little less daunting with some text recognition.
So which part do we draw?
All of it.
Do you draw where that out?
Do we have to draw the little curvy thing?
What?
The mRNA? I mean the ribosome? This thing.
Yeah,
That's the ribosome.
yeah, that's like a huge important part of the process.
That's the ribosome. It's like it represents the ribosome. The ribosome. It's like a big
That was the tRNA. That helped.
I don't know, what is that ribosome?
Let's see what recognized handwriting does.
The
Woo,
UBC
that's not bad.
is the tRNA. That was what was used to transfer like this onto this to read it. To translate AUG into whatever it's like. And once the ribosome moves on,
Anticodon
the method
to
is still there. The translation has been done. So
codon.
this can use this, so it goes
What else do I need? Amino acids form peptide bond. It doesn't movies, but it does move. One, not L. One codon over.
Oh, I got it. I might give you.
No.
I need some fat glucose. I'm about to eat a Rice Krispie treat. Glucose. Diabetes? No, it's just.
That gentleman. There's a constant stream of vaguely disturbing conversation. There you go.
Oh, so when this is stop, you just
When it says stop, you stop.
so do you write every part?
Pardon? Yeah, we're going to do the last phase, and the last phase is how does it say stop? Yes. So you're just doing elongation.
So elongation is like moving one by one.
Mm-hmm.
Okay.
Making the actual protein.
Yeah.
Does everybody have this part of the diagram now? Okay, because I'm gonna continue elongation. You don't have to draw it because how can you animate a piece of paper? But you would then take it, moves over, chunk, 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 chunk. That goes away. New one comes in. GGG. We made one up because I was confused. So CCC. I believe GGG codes for glycine. Yeah, so that would come in. Boom. Chunk, chunk. We would get the peptide bond forming. And this would move over. Oop. Chunk, chunk. Now this would fall away. And now we are almost at the end. Look up on your table. What does UAG code for? Stop. And there's no amino acid for that. It just literally means stop. How many stop codons are there?
3.
There are 3. There's only one start codon, and that's AUG, that codes for methionine. But there are 3 stop codons, and they're known as amber, ochre, and umber. They have colorful names. Also, I want you to just stare at the table for a moment.
Okay.
Do you notice anything efficient, non-efficient, or patterns in it?
They start with the same letter.
Pardon?
They start with the same letter.
What starts with the same letter?
The groups.
The basis?
The bases are, so give me an example.
What is this? First base is U. They all start with U, and then you can find the second base with the chart, and then the third base.
Oh, I see what you mean, yeah. And they've done that to organize it. I thought you were getting at a little something else. If they all start with U, is there anything that you can notice in terms of the code and how efficient this code is?
If they all start with U, they're
If it starts with U, do you know what amino acid it is?
No.
It could be a lot of things. If it starts with U, let's say CU, CU, do you know what amino acid it is?
Yes.
Yeah, what is it?
Leucine.
Leucine. And the last one actually doesn't matter. It could be CUU, CUC, CUA, CUG. It's all leucine. The code has redundancy in it. So, for example, if you get a mutation in your DNA and it changes a U from CUU to CUC, will that change the product it makes? No. It's called a silent mutation, and they occur all the time. And because it has no effect on the organism, they happen at a fairly steady rate. This is how we know things like, oh, we last shared a common ancestor with a pea plant, 1.3 million years ago, because the amount of silent mutations that have accumulated in the same gene in both of our organisms. This is also gives us a little clue into the past. We think the DNA code used to only be 2 letters and not 3. It added the 3 letters to add some extra amino acids in there. At some point, the code changed. But biochemistry doesn't leave fossils. And so we can only look at it and look at the pattern and try and make some guesses. You could actually code for most things with only a 2-letter code, but you don't quite have enough for the amount of amino acids. How many amino acids are in there? A lot.
So
Mm-hmm.
does that mean we could have 4 in the future?
If you had 4, would it help you at all?
Not much.
Not much, because you could already code for more amino acids with this. Does anybody know very quickly using math? If you have a 3-letter code, how many amino acids could you code for?
27.
More than 37. Pardon?
81.
Don't think it's 81. I mean, you can go through and count. 1, 2, 3, 4. And there's 1, 2, 3, 4 boxes. 4 across, 4 down. 4 times 4 is 16. 4 times 16? 64. This is a total number of 64 codes. There are not 64 amino acids. There's a little bit over than a little more than 20. And you can also see where they probably mutated. CU codes for one thing, AU codes for one thing, GU codes for one thing, but UG is cysteine, a stop codon, and tryptophan. That is the only place tryptophan is coded for. That is probably a recent addition. It used to be probably either all cysteine or all cysteine and stop. And I only mention this because again, biochemistry leaves no fossils. Why 3 codes? Adding a 4th one wouldn't actually help any, it would just be extra work. You already have more than what you need. And it also has a little bit of a safety feature. If more than one codes for the same thing, then at least some types of mutations aren't harmful. It might be a little protective. Anyway, this last part, where it comes together, it hits the stop codon, the last mRNA floats away, the mRNA floats away, the ribosome floats away in all its separate pieces, and you're left with your single amino acid strand is the final result. Everything floats away.
When you get to the last one.
Yep. And then it's ready to start again. The tRNAs will go pick up amino acids again and get ready for the next one. The ribosome will go looking for another mRNA to read. The mRNA now can be reread from something else if they're long enough, which most of them are. You actually can have more than one ribosome going along at a time. So one's reading, and then another one's coming in behind it, and then another one's coming behind that one, and like a little train. Yep.
How long are the amino acid strands normally?
Oh, they can either be from tens to hundreds. Sometimes thousands. So big. They can be very big. Yep.
What about the last one? Like the UAG does that not bond an amino acid? Like
Nope. It just means stop. So it's bonding the little rRNA inside the ribosome. When it hits that particular codon, it actually forces the ribosome to break off. So it is hard coded in there. Termination.
The ribosome just leaves.
Ribosome hits stop codon. Ribosome detaches from mRNA. tRNAs detach from amino acids. Peptide/protein. Chain connected amino acid. Have you heard the word polymer before? Polymer. What does poly mean?
More than 3.
Yeah, that works. Many. If your definition of many is more than 3, that'll work. If your definition of many is 3. But, yeah, but 3 amino acid peptide would still be considered a polymer. Technically, actually in biochem, 2 peptide is technically a polymer. Means many, just in the general root. What does mer mean? Pardon? A substance? Mer is, polymer is, just stands for a piece. So polymer, many pieces. These are polymer of protein. Many pieces are amino acids when put together make up a polymer. The polymer is a protein. When you make nucleotides connect together, you make a polymer called If you put a bunch of nucleotides together, DNA or RNA. If you put a bunch of fatty acids together, you get a lipid.
Yeah.
What'd you say?
I said glycerol.
You put it together with glycol.
Okay.
Yep. Hold it. No, glycerin. What's the structure of glycol?
Glycerol.
Oh, glycerol. Yeah. Yeah. So, draw the end result determination. That is your last phase. And it is, in fact, phase 3.
What's phase 2?
Phase 2 is elongation.
What was phase
initiation.
Oh. Oh.
Yes.
Does that mean the last colon never gets translated?
This one here?
Yeah.
No. Well, it does in that it is interpreted to stop.
Oh, so it.
So there's no amino acid.
Okay.
It doesn't code for anything. It's like the period at the end of a sentence. That means no more. It's like when your parents use the angry voice. It's time to stop. You're arguing, and they said no, and you're arguing, and they said no, and then they say no in the way that means that things are about to get dangerous, and they're going to get out that thing. Leather strap, little barbed hooks on it. Only my parents? Okay. I was kidding. If my parents ever listened to any of my lectures, that would be really bad. Yeah.
For termination, the amino acids that are like connected through peptide bonds, are they still like connected to the like AUG?
No, they're gone. It's all disconnected.
Oh, okay.
Yep.
So there is separate
Gone.
strands.
Everything's separated. This can now go do its job. So this could be an enzyme. It'll all go and start enzyming. It could be a hormone, in which case it's going to be packaged by the Golgi apparatus into a vesicle and exported outside the cell. This could be a part of the cell. It could be a piece. It could be a motor protein. It could be that little guy that walks down the cell carrying the thing. It could be all sorts of things, and it's going to go do its job now. It's done. It's built. It's ready to go. It's a little bit of a lie. Biochem, it could combine with other proteins and get packaged in different ways and make bigger proteins. But for our purposes, it's done. It's done. All that labeling down there, you don't have to do because we did it as we did this. Good? Excellent. On the next page, write in the mRNA to the tRNA and then the amino acid sequence. And just so that you become familiar with it, oh, is yours written on too here? Sorry I didn't erase that before I printed. This is a different way of writing the table, and whatever university you go to, the most familiar one I've seen is the box table, but I really like this one. This is the first letter. And you go, oh, it's G-A-U. That's pretty. It is C-A-G. Glycine. And so you can go through and do all of them as a little round table. They have symbols for start and stop. But as well, the amino acids, in addition to their shortened three-letter form, alanine, aspartame, glutamate, glycine, phenylalanine, leucine, serine, tyrosine, they also have letters. And so sometimes if we want to be really, really quick, we can just write them out as a series of letters. We're not going to do that, so you can ignore the letters.
Do they all start with these letters?
Pardon?
Do they all start with these letters?
Well, like arginine has an R because there's too many that have A's, so they just pick a letter for them sometimes. Yeah.
Or actually,
Yeah.
let me double check.
You know how the codons meant to start with AUG?
Yep.
Here, the mRNA starts with AUC. Change it to G.
Oh, yeah. This greatly annoys me. I will grab examples from places, and it seems that people don't know that. And so they do examples that don't start with it. When I do it, I make it so it has it. But if I grab this diagram, because I don't have the patience to make it, just go with AUC and know deep in your heart it is wrong.
Yes, I do.
We could pretend it's in the middle of the amino acid somewhere, of the mRNA somewhere. Yes.
So would A be, when the A is mRNA, is like the first one, would the tRNA be T or U?
Oh, so no, it would not be TRU
No,
or T. Hold it. Here, you mean?
no, the tRNA.
So what's that would be?
U.
U,
So you're right, it is U.
A, G,
UAG.
and what does AUC code for?
Glycine.
A, U, oh, not glycine. AUC is AUC isoleucine.
So you, for the circle one, you use the tRNA?
No, you always use the
Oh,
mRNA.
you just,
Always. This is just getting the tRNA and then seeing if you get confused enough to use it. So I've done the first one. You can do the other ones.
oh, I found mine. What's happening?
Also,
Mm-hmm.
the last one, should we just do it as it is, or should we make it into a stop?
No, you mean this one?
Like the last one on the screen, like the code one.
Here?
Yeah.
No. We're just going to pretend that this is in the middle somewhere.
Okay.
Yeah. Yes?
On the second one, does that stop it?
Where?
The yellow one, it's like doesn't that stop?
UAG.
That's an initiator.
I don't see UAG here. Where's
In the
But
you?
that's
Oh, there it is.
an initiator.
Isn't the
Yeah.
So, mRNA, U, A, G, codes for stop. Yeah. But you stopped.
But we don't have to do it.
You stopped. You just gave away the trick to the rest of the class. Well done.
also you wasn't the red?
But you stopped. Yeah, you don't do that. It doesn't matter. Now you could do it as an intellectual exercise of what would those code for if they coded for a thing. But yeah, it stops. Now this actually illustrates. Well, I will let you write. But if you get a mutation and an amino acid becomes a different amino acid, could that protein still function? Yeah, one amino acid different? Might still work. Maybe it'll work better. Probably not. But it might. That's how evolution happens. But if you turn it into a stop codon, is that protein going to work? Probably not. That is a deleterious mutation. That organism is in trouble if that protein is in any way essential for life. Yeah. So mutations are almost always bad. We talk about evolution improving things, but evolution only improves things by killing everything that doesn't improve. It's built on the blood of species. There are more species dead and extinct than there are alive.
It's gonna be at the test.
No, this is new.
Okay.
Yeah. Yeah. I always really like this part about him because it's just codes. You look on the table, it's so easy. Nice.
You could like write sentences.
Hmm?
You could like write sentences.
Good, yeah. We don't have all the letters in the alphabet if you go by the letter phase. But if you see someone with a nerdy T-shirt that just says a bunch of amino acids on it, often if you look up the one-letter code for it, it actually said something. Okay. Yeah. Thank you very much. Enjoy. Enjoy.